Today we're going to be talking about higher degree polynomials. Now when we say higher degree polynomials, what that means is we have this foundation where we started talking about the y equals x squared function, which is the quadratic functions. That's what we've seen before. We've also seen cubic functions, y equals x cubed or x to the third power. And we can continue on with these exponents, these degrees on the input x. And we can increase the degrees and we can look at these higher degree polynomials. And so in particular, it's not written here, and maybe you've seen or looked at polynomials before, but a polynomial is essentially a function where the exponents on the x, on the input, are whole numbers. So they're not zero, they're not negatives, they're not fractions. So that means we don't have x in the denominator of fractions, we don't have square roots of x. It's all just nice x to the power of 2, x to the power of 3, and then you might have some adding, subtracting, multiplying, some coefficients there. So let's write these are whole number exponents on x. So when we say the degree of a polynomial, what we are referring to is the highest power on x. So for example, if we look at these polynomials down here, we can look at their shapes and identify some similarities, some differences, and all that. Let's first take a look and write out their degrees. So this first one is the function f of x equal to x squared plus 4x plus 4. When we say the degree, we're looking at the highest power on x. So we see this first term has a power exponent of 2. The second one has an exponent of 1 on the x. And there's technically on this last one an exponent of 0, because x to the power of 0 is 1. Anything to the power of 0 is 1. So the highest degree is 2. And on the next one, we have it written slightly differently. You have a number factored out, but it's still a polynomial. It's all adding, subtracting, multiplying. And the highest exponent on x is 4, so that's the degree. On the next one, the degree again is 4 because that is the highest exponent on x. And then the last one, the degree is 8. So now we want to see what do all these degrees have in common, and you might notice it right now by just looking at it. We have 2, 4, 4, and 8, and not in any particular order. We just want to see the relationship between these. And you might have noticed that the relationship between these is that they are all even. And so you might see some similarities between these graphs. And I'll just list out a few of those similarities, and I'm sure you are able to see some other ones. So we have that all these graphs, you might see we would say open up. So they're all going up to positive infinity here. Remember how we talked about parabolas and quadratics, and those parabolas open up? Well, these graphs all open up. So we can say they all open up. They also all have minimum values or local minimum values. So you can see here we have the local minimum on that first one. That's a quadratic, so that's the vertex. This one has some local minimum values over here. This one has some local minimum values over here. And then the last one has some other local minimum values. You can maybe make an argument if that one's a local minimum. But they all have local minimum values. And again, you might be able to identify some other similarities that you can see here between these. But now we also want to look at the differences between each of these graphs and each of these functions. So looking at these graphs, you might see some similarities, but the difficulty is putting that into words. So similarities, we just got off talking about local minimum values, and that's a similarity between these graphs, but it's also a difference because this first graph has 1 local minimum value. The second graph has 2 local minimum values. The third one has 2. So they have different number of minimum values. And then they also have, some of them even have maximum values, right? This one has a local maximum value here and a local maximum value here on the third one. And so they have different number of minimums, number of maximums. So let's say the mins and maxes differ. And so because there are different minimums and maximums, and some have maximums, some don't have maximums, we can say that there are more or less like intervals of increasing and decreasing, or like those changes in the slope. So you can say there are different turning points or different number of turning points. They also have different ranges. We could also say that they have different number of x-intercepts. So with all of these, they have, like this first one on the quadratic has one x-intercept. On the second one, you can count 1, 2, 3 x-intercepts. On the third one, there's 1, 2, 3, 4. On the last one, there's 2 x-intercepts. So we have a varying number of x-intercepts. And if you recognize or see any other differences, I invite you to write them down and to make note of them. And so you want to think about this question next is, what would happen if the leading coefficient was negative in front? So notice with all of these, the leading coefficient is positive. On the first one, and in fact on all of them except for the second one, the leading coefficient is just positive 1. On the second one, it's positive 0.1, but they're all positive coefficients. So the question is, what would happen if it was negative? And we can think back to what happens with the quadratics when we make that a negative. When the a is negative on the quadratic, it opens down. It is a reflection over that x-axis. And it's kind of the same thing that happens with these ones. They will sort of flip upside down. So instead of opening up, they will now open down. So on the next set of graphs, we have x cubed minus x is the first one, x to the fifth plus 7x cubed, and so on. But let's identify the degrees of these, and then we'll ask those same questions on these ones that we asked on the last set. So the degree of this first one, the highest exponent on x is 3. The degree on the second one, the highest exponent on x is 5. The degree of the third one is 7. The degree of the last one is 5 again. And so looking at these degrees and kind of comparing that to the degrees of the other ones, you might recognize that these degrees are all odd. And you might identify the overall shape or some similarities between these graphs, and they all sort of kind of look like cubics. So they're all cubic-like. They're not exactly cubics because, you have degree of 5, degree of 7, which is different than a cubic because cubic is degree of 3. What's happening is they sort of start and end in opposite directions. So we can say start and end in opposite directions. And that's a contrast with the even functions, the even degree polynomials, because those ones, if we scroll back up, those ones always said open up. So they all start and stop, or start and end, sort of with going up to positive infinity. But these other ones, you have it going down to negative infinity on the left, and then going up to positive infinity on the right. So we have that they sort of start and end in these different directions. And then we can identify some differences among these graphs. And now I invite you to pause right here and to try to identify some of the differences yourself that you see within these graphs, and maybe compare that with the differences in the even set above. So hopefully you went through and at least brainstormed or created a list or some ideas for the differences in each of these graphs or each of the functions. And we can say some of the similar or same differences that we said earlier. All these graphs sort of have these varying minimums and maximums. Like this first one has one minimum or local minimum, one local maximum. Same thing with this other one, one local, one maximum, one local minimum. And then that last one has a lot of different local minimums and maximums throughout it that are different than the other ones. So we can say the maxes and mins vary. We can also talk about the x-intercepts as well. Like this one has 1, 2 x-intercepts. This one also has 1, 2 x-intercepts. This one just has 1 x-intercept. This one has, if we count 1, 2, 3, 4, 5 x-intercepts. And so they all vary in those x-intercepts, and they all vary in sort of like the maxes and the mins and how many maxes and mins that they have. So you can think of it also as like the number of bumps or like hills, valleys, number of swoops, number of humps. And then also, like we just talked about, the number of x-intercepts also vary. And so the question again is, what would happen if we made the leading coefficient negative? Because look, on all of these, the leading coefficient is 1. And when we say leading coefficient, remember we're talking about the coefficient on the term, the x, that has the highest exponent, the highest power. So whenever we say what the degree is, like this one is 3, we're referring to the leading coefficient to be the coefficient on that term, the x cubed. So if we make that leading coefficient out front negative, just like with the quadratics and just like with the even functions, it will essentially do like a reflection over the x-axis. So it would be kind of like a vertical reflection. And so notice all of these sort of start on the left, they have their graph going down, and then on the right they have the graph going up. So instead it would be, something like this, where it'd be flipped. So it would start from the positive infinity going to the left, and then it would go down to the negative infinity going to the right. So let's summarize some of this information, these similarities and differences, in a nice table format. So first, one nice notation that we're going to be using to help describe some of these behaviors of these graphs of functions is that we'll use this notation here that says x arrow infinity. So what that means is that you're looking at the behavior of x, so what's happening with x? Well, it is approaching affinity. So that's what the arrow means. It means you're approaching or getting close to. So when we say x is approaching infinity, then that means that we're looking at the right side of the graph. When we say x is approaching negative infinity, that means we're now going to the left. We're looking at the left side of the graph because that's where negative infinity is. And then we'll use that notation to describe some of the end behaviors. So we'll break it up into 4 cases. The first case is if you have an even degree and the leading coefficient a is positive. So remember that a here is the leading coefficient. So if even degree leading coefficient is positive, then you have your graph that's like opening up. And the domain here, it's always going to be negative infinity to positive infinity. And in fact, for all polynomials, we can plug in any number as our input. It doesn't matter what the number is. It could be 5, it could be negative 22, it could be the square root of pi. You can plug in any number you want. And so the domain is always going to be negative infinity to positive infinity. Because usually the restrictions that we have on domains are if we're dividing by 0 or if we're taking the square root of a negative number. We have to be careful of those things. But here, we don't have any square roots. We don't have any dividing. It's all adding, subtracting, multiplying. And we can do that with any number that we want. So the domain of all polynomials are negative infinity to positive infinity. And so for the range on this first one, let's identify or call what this vertex is, right? That minimum value. Let's call this the HK from when we were talking about quadratics. And so if this is the point HK, then the range here, well, we know it's going to be opening up. So it goes all the way to positive infinity as like that top bound. And then the lower bound is going to be that k value because we're looking at the y. So it goes as low as k. So the range is from k to infinity. We use a bracket because we actually include that point or that y value of k. And then the end behaviors, so this is saying as x goes to the right. So if you follow the graph to the right, what is the output of the graph doing? Well, the output of the graph, the height is going up. It's increasing to infinity as well. So as x goes to infinity, so as we go to the right side of the graph is going up to infinity. And then on the other hand, as we go to the left, as x goes to negative infinity, the graph also still goes up to positive infinity. And now the next case is even degree, but the a, the leading coefficient, is negative. It's less than 0. So what that looks like is it's now kind of like a parabola, but it's opening down now. So to identify the range, let's call this point the maximum point, which is hk. On quadratics, it's the vertex, but sometimes when you get higher degrees, you might see different number of maxes and mins and everything. So the range here, the lowest the graph goes is it goes all the way down to negative infinity because it goes down forever. And the highest it goes is that y value of that vertex, which is the k. And it actually includes that point, so we use the bracket. And the end behaviors, they're going to be the same as each other, right? The right hand and the left hand sides are going to be the same behavior. They're both going down to negative infinity, which is a contrast from the first case where it was going up to positive infinity. And now for the odd degree, they all generally have this same shape. There might be different swoops and turning points and all that, but they all have the same general idea. So we're looking at odd degree where a is positive, that leading coefficient is positive. So the range here, it actually goes down to negative infinity and it goes up to negative infinity. So on odd degree polynomials, that range is going to be positive infinity to negative infinity. And so then the end behavior here, so as x goes to positive infinity, the right hand side, we can see what is the graph doing, what is the y values doing. So the y values are going up, they're increasing. So as x goes to the right, the graph increases, it goes up. And then as x goes to the left, you can see the arrows going down, so the graph is going down to negative infinity on the left hand side. So when a is positive, the right hand side is going up. And then now when a is negative, when a is less than 0, we can take a look at, well, the range is going to be the same. That's going to be negative infinity to positive infinity. The end behaviors, the right hand side, that's now going down to negative infinity. And the left hand side is going up to positive infinity. So you can see that when we swap the sign of a, of the leading coefficient, then that swaps the end behaviors. So on the even degrees, it's positive when a is positive, so it's going up to positive infinity. And then when a is negative, it's both sides, the left and right hand side, are going down to negative infinity. And then on the odd degree ones, when a is positive, the right hand side is positive. When a is negative, the right hand side is negative. So I like to think about it and remind myself that the a, whether it's positive or negative, determines the right hand behavior of the odd degree polynomials.